now we will see the stability analysis for the Crank-Nicolson method. So we'll see that the Crank-Nicolson method is unconditionally stable. So the Crank-Nicolson method is unconditionally stable. So this we will see. So let us recall that what was the scheme for this. So we have seen a matrix was something like that. Some matrix was there, and this was un plus 1, and this was some matrix was there at un, and plus some vector was there. So I would say this matrix as A and this matrix as B. And see in the problem what we have seen, in the problem the B was not there because the boundary condition was 0. That's why B was not present. The vector B was not present here. So we have the matrix A u at n plus 1 equals to B and u at n plus B. So this is the scheme that we have. Now what we'll do, we'll define error. We'll define the error like that. We'll say that the error, the E at n plus 1, the error vector at n plus 1 is the difference of the computed value minus the original value. So this is your computed value of u, this is your computed value of u at x at tn plus 1, and whole x means this is nothing but this is the computed value of u vector at tn plus 1, and this is your original value of u, original value of u at tn plus 1. So this is how the error is calculated. So see, let's say this is your 1. So what we are seeing that equation 1, since we are estimating our differential equation, so what we want that the computed value of u should also satisfy the equation 1. So basically what we want, that we want this, that A u computed is equals to B u computed plus the vector B. Okay, so this we want. Since we are saying that error goes to 0 or something happens like that, so we want our solution to be satisfied by the computed value of u also. So now we can compute the error. So we can compute the error by just subtracting 2 and 1. So if we'll do this, so we'll get 2 minus 1 will give me the A into error at n plus 1 equals to B and error at n, and that B we will cancelled. So it means that we are getting the error vector n plus 1 is equals to A inverse B we can clearly see the A is invertible matrix, so that's why I'm taking the inverse. So this. So from Lax-Richtmeier theorem, what we know, so from Lax-Richtmeier theorem, we know the method is stable the method is stable if and only if it is convergent. This. So here let's see that when does the method will be stable. So we want that since we are supposing that the error it is we want to prove that the method is stable for what value of r the method is stable. So from Lax-Richtmeier theorem we will suppose that the method is convergent, so we will suppose that the error goes to 0. So as error will goes to 0, let's take the norm, sup norm. So this will be the norm of A inverse B epsilon n norm. This is also sup norm. So this is less than equals to the norm of A inverse B into the norm of the error. Now in the same way, if we compute, this is less than equals to A inverse B and A inverse B. This is true for all n. A inverse B into error at n minus 1. N minus 1. So this will come square. So this is nothing but. So this is nothing but. This. So now we have like this, so we have a sequence of this. So what we will do, we'll go to the, so this will be from here what we can write. So this will be that the error will be less than equals to, so this will be less than equals to, we got A inverse B whole square. So in the same way, if we will proceed, we'll get that A inverse B, and this will be, if we go to the 0, so it will be n plus 1. So see, if this will goes to 0, so it means that this has to goes to 0, this has to converge. So this should converge. So what it means? What it means? The spectrum of this matrix must have to be less than 1. So then only, as we know, if the spectrum of this is less than 1, then it will converge. So we got this, that this should be the required sufficient and necessary condition for this method to be stable. Now we'll compute that what is the eigenvalue of A inverse B. So we will calculate the eigenvalue of the matrix A inverse B. Yes. Okay, so let us calculate this. So what is the matrix A? So the matrix A was 2 plus 2r minus r 0 0, and the size was n minus 1 cross n minus 1, I think n minus 1 this is minus r, 2 plus 2r minus r, 0, this is minus r and 2 plus 2r. So this is what the matrix A is, and the eigenvalue of a tridiagonal system, let's see the eigenvalue of a tridiagonal system. If the matrix is like this, in this A, B, then we have some AB like this, and let's say here again B, A, C, then again B, A, C, like this. If you have a tridiagonal system with A in the diagonal and B in the subdiagonal and C in the superdiagonal, so it will be C. Yes. So B in the subdiagonal and C will be then the superdiagonal. Then the eigenvalue lambda s is given by A plus square root of BC cosine of pi s by n plus, the matrix size is n cross n. So where this s is equals to 1, 2, n. Okay, so you will calculate the eigenvalue of A, eigenvalue of B. So the eigenvalue of A would be, so the eigenvalue of A, so here for A, let's calculate for A. So A would be 2 plus 2r, B is equals to C is equals to minus r. So if we'll calculate lambda of A, it will be so let's AS, because I will write AS, so let's write it in this way, lambda AS. So this will be 2 plus 2r plus 2r square, the square root of BC, so this cosine of pi s by n, and this was n plus 1. Yeah, so this would be n because the size of the matrix is n minus 1. So this will be your 2 plus 2r plus it's minus, is it minus and not 2, a bit of this, yes. So 2 plus 2r into 2r cosine of pi s by n. So this will be the eigenvalue of A. If we calculate the eigenvalue of B, the B matrix was in here, here and here. So this was 2 plus 2 minus 2r, this was r, and here r was there. So for this, A equals to 2 minus 2r, B equals to C equals to r. So if we calculate lambda s of B, it will be 2 minus 2r plus 2r cosine of pi s by n. So this. So now the eigenvalue of A inverse B. So the eigenvalue of A inverse B would be the lambda s B by lambda s A. So that is nothing but 2 minus 2r plus 2r cosine pi s by n divided by 2 plus 2r plus 2r cosine pi s by n. So this is the eigenvalue of this. So here S is equals to 1, 2 and minus 1. So now see what we want, that the maximum of the eigenvalue should be less than 1. So it means that what we got from the last expression, so the matrix will, the method will be stable. The method will be stable if this, that 2 minus 2r plus 2 cosine pi s by n divided by 2 plus 2r plus 2r cosine pi s by n, this mod will be less than 1. Yes. So what it means? This means that this fraction divided by 2 plus 2r plus 2r cosine pi s by n is less than 1 and bigger than minus 1. Now let us consider this inequality, the plus side, this inequality. So this will give me that 2 minus 2r plus 2r cosine pi s by n is less than 2 plus 2r plus 2r cosine pi s by n, and this is true for each s equals to 1, 2,